Nice. Ah, chiudo? Ho lasciato. Chiudiamo, qualcun altro che... Okay. Good afternoon, everyone. So it's a big pleasure to have here with us Silvia Onorato. Silvia got her master thesis here in Bologna, working with me and Emma on multiple scalar populations in globular clusters. Then, so she fell in love so much with resolved stellar population, and so she decided to do her PhD on extragalactic astronomy, on high redshift quasars. And so now she's a third year PhD student, third year PhD student at the Leiden University, working with John and Naui. And today she's going to tell us something about high redshift quasars and her ongoing PhD work.
Thank you, Mario. You have stolen some of my lines. Okay, so good morning, everyone. As Mario said, I'm Silvia Onorato. I come from Leiden University, where I'm a PhD student working with John Naui in the Enigma group. And my work focuses on constraining the Epoch reionization and supermassive black hole growth using redshift. So I wanted to start just with a huge thank you to Mario for giving me the opportunity to be here today, because as he said, I'm really happy and really excited to be here because I was a student here, and I prepared just a few photos, so lame photo shaming first. So here we can see part of my class during my bachelor at the Loiano telescope with Luca Parmitano. This is the class of Professors Buzzoni that here during the master, and this is my bachelor party, the only one that I did in person because then my master was during COVID times, as we can see here. Anyway, now we can move back to science. And of course, I cannot start my presentation without these slides. I will be shorter. So when the universe formed after the Big Bang, it was a hot ionized plasma that with time started to expand and cool adiabatically until it reached the temperature necessary to form the first atoms. Going through the first very important stage of the universe, there is the recombination phase transition, which also released the cosmic. After this, the universe experimented the so-called dark ages. So the universe was dark, there were no sources yet emitting photons, and with time it started to get colder and colder. Finally, after a while, we have the formation of the first galaxies into the first dark matter-driven structures. And into this system, the first stars and black holes started to emit ionized photons, allowing us to go to the second important stage of the universe, the reionization phase transition. And then the universe got again fully ionized. So in my work, as probably we already understood, I'm interested in studying this specific epoch. What can we do? How can we study this epoch? We can target bright background quasars around redshift 7 and 8. But really, how? How can we do that? So how the spectrum of a quasar look like at different redshift going close to the Epoch reionization? So this is a spectrum of a quasar in a relatively local universe. But once we move to higher redshift, so going already a redshift around 3, the Lyman alpha forest starts to appear. What is the Lyman alpha forest? So basically the radiation from the quasar is traveling towards us. And during his way, is finding clouds of neutral hydrogen placed at different redshift, which are creating absorption and producing this feature into the quasar spectrum. Of course, this is helpful for us because this allows us to study the fractional neutral hydrogen. But then, when we go to higher redshift, this feature starts to disappear because it gets opaque at redshift higher than 6. And then we have the Gunn-Peterson probe. So now, how can we study the fractional neutral hydrogen and other parameters when we get around this redshift? Well, fortunately, there are other features we can use. These features are still imprinted into quasar spectra, and they are called damping wings and proximity zones. I'm going to say something more about that so to let you understand what they are. So let's start with the damping wings. So let's consider a universe around redshift 7. So we have a universe that starts to get ionized, but is mostly neutral. So in this condition, this kind of feature is imprinted into quasar spectra. It's basically an absorption red word of the Lyman alpha line. And this is due to the fact that the Lyman alpha is a resonance line. And when the fraction of neutral hydrogen is so high, like in this case, we have a fraction that is around 10 to the minus 1, even the tails of the line are getting absorbed, producing this kind of effect. For the proximity zone, we move to a relatively lower redshift, so we are around the redshift 6, and these other kind of features appear in the quasar spectrum. So basically, they are regions of enhanced ionization from the quasars in an already ionized IgM. The important thing is that these effects, they both tell us something about the fraction of neutral hydrogen. For the goal of my talk today, I will not focus on the damping wings. I will just focus on the proximity zones, and I will tell something more about that. So let's just picture this situation. So the quasar is a powerful source, emitting ionizing photons. These photons are able to produce a kind of a bubble of over-ionized IgM around the quasar itself, something like this. We can picture these as the strong spheres around all the stars. The size of this bubble can be described in this formula and depends on some properties of the quasar, such as quasar luminosity, the lifetime, and the fractional neutral hydrogen. But unfortunately, we cannot measure this from the spectrum there. So it's in this context that we define the proximity zone as the region blue word of the Lyman alpha line, and we use this as a proxy to study the bubble, and then place constraints on both the quasar lifetime and the fractional neutral hydrogen. I want you to see now what is the effect of the quasar lifetime and the fractional neutral hydrogen on the quasar spectrum. So here I want to show you an animation. In this particular case, we are keeping fixed the fractional neutral hydrogen, so it's neutral, and we are increasing the quasar lifetime. So once this quantity increases, the feature starts to get every time even more visible. This effect is essentially the same if we do the animation the other way around. So if we keep fixing the quasar lifetime and we change the fractional neutral hydrogen, at the end of the day, we will have the same exact results. This is just to tell you that there's a degeneracy between these two parameters, that this is something we should take into account and we should break it. For the goal of my talk today, I only want you to keep in mind that the proximity zone increases with increasing the quasar lifetime. But as I said, the final picture is much more complex than this, because at this redshift, the proximity zone reflects a combination of both the quasar lifetime and the patchy topology of the IgM. But for today, this is the important thing you need to know. Finally now, so what is the goal of my work? What I want to do? I'm interested in studying the Epoch reionization, and in particular, as we said, the fractional neutral hydrogen. So the idea ideally would be to kind of recreate the history of reionization and then place constraints on this quantity at different redshift. I'm interested in studying the quasar lifetime, and then I also would like to understand how did the supermassive black hole grow at redshift higher than 6. What we do today is focusing on these proximity zone size measurements that then will lead us to answer the second one of these questions. Okay, now practically, what did I do so far? We have built a sample of quasars. We can call this the Enigma sample, because my group is the Enigma group. And is done with 45 quasars, a redshift between 6.5 and 7.64. They are relatively bright objects. They span in this magnitude range. The sample contains 12 BIL. So if you're not familiar, this means broad absorption lines. So these are objects with broad lines. So that in principle, we want to exclude from the analysis because this feature could bias the final results. So in the end, we just perform this analysis on 35 objects. This is just a lame advertisement. I have reduced the data with Pipit, which is a software developed by my supervisor and other collaborators. And all the spectra have medium moderate spectral resolution coming from different ground-based facilities. This is a quick overview. I don't really want you to learn anything from this slide. It's just the spectrum with amazing colors, if I can say. And this other plot. And the main results I will just spend a couple of more words about is this one, which is the composite spectrum. And is one of the main results that I've discussed in the first publication. So this is, as I say here, a revisited version, because this is something I'm still working on, trying to improve it. The composite spectrum is just an average spectrum that we get stacking together all the spectra that we have. In particular, in this case, I have excluded the BAS for the same reason I've described before, but actually there's not really a big difference between excluding or including the source. It just doesn't matter that much. And then what we do is just taking all the spectra, moving them to the rest frame, define a new wavelength grid. Yes, the new wavelength grid, like rebeaming all the spectra to have the same spectral resolution that we set to dvpx 110 km per second. And then we normalize the spectrum at 1450 angstrom. To improve the final results, we also apply some masks, like masking out the regions of the volume absorption, bad center-to-noise ratio, bad error vector, and spikes, whatever. And then the final results that finally we get is this black curve here that is compared with other composite spectra coming from the literature. So basically what you see here are the average UV spectral properties of quasars at redshift higher than 6.5. But the interesting thing is that from this comparison here, you don't really see big differences between composite created at higher redshift and composite created at lower redshift. So this means that the composite spectrum, the spectra in general, the spectrum of a quasar doesn't really change through the cosmic time, which is a big deal. I mean, is a good result. Okay, now we can move back to the rest. And if you're interested in learning more about this first part of the work, other advertisement, check it out, this paper that we submitted a few months ago. So why is this sample so interesting? Well, the answer is, with this work, we are pushing the limit of knowledge about proximity zone to even higher redshift. Because with this work, we are targeting sources that didn't have proximity zone measurements before. So we're doing something like to push the knowledge to higher redshift. Then practically now, how do we do this kind of analysis? What is the first step for the proximity zones? The first thing we need to do is recreate the quasar continuum. So we are at higher redshift. So after the Lyman alpha, the spectrum is absorbed. And we need to know how should be the spectrum after the Lyman alpha. So what we do is applying an algorithm of principal component analysis. This is an example coming from Fred Davis' work of the quasar Pisco. Basically, this algorithm takes the red part of the spectrum, we train the algorithm, and then we predict the blue unabsorbed part. This quasar is also in my sample. So this is basically the same source, but this is a plot that we have done now. Okay, so once we do this, we finally have our continuum estimates, and now we can use these estimates to apply the definition of proximity zone. So as I already mentioned at the beginning of the talk, we define the proximity zone as the region blueward of the Lyman alpha line. Lyman alpha that is set here in 0, until where the continuum normalized flux, which is the black curve, but smoothed by a 20 angstrom boxcar filter in observed frame, which is the red line, first drops below a level of flux of 10%. 10%, which is set from this dashed yellow line. So once this condition is satisfied, we have set our measurement of proximity zone, which is here. Then we also take into account some sources of uncertainty, like we have the uncertainty on the redshift, which is taken into account here, is on the position of the Lyman alpha line. Then we have the uncertainty on the continuum estimates, which comes from the PCA reconstruction, which might be not super precise. And then we have the uncertainty on the pixel size, which comes from the spectrum, from the instruments used. We can do this for all the sources in our sample, and finally, we get that all our measurements span in this range. We want now to test how good are these estimates. So we've done a couple of scatter plots. So the idea is some of these sources were already analyzed, in other words, from the literature. So we just compare our measurements with other measurements from the literature, and I would say that this scatter plot seems to show that there's a good consistency between these two measurements. Then I also do the same considering the EX230 sample. So the idea is just, we don't want to limit this analysis to the Enigma sample. We want to have a homogeneous work. So if we have the chance, it's nice to reproduce the same analysis on other samples, and we did for the EX230. That was already analyzed in this paper from Sindhu Satyavolu to 2023. Also in this case, there's a good agreement between my measurements and other people's measurements. So the method seems good. We can finally discuss a few implications. So the first important plot is this one, which shows you the distribution of the proximity zone with the luminosity, color-coded with the redshift. So here we have all the samples that I've already mentioned. So the Enigma sample, this is another sample coming from Dominika Durovčíková work, so it's just a couple of objects analyzed with fire, and the EX230 sample, and then we compare them with other results coming from others working in literature. Here you also see these two curves. They come from Christina Eiler's work of 2017, in which we are showing here what is the expected evolution in case we consider an IgM mostly neutral or mostly ionized. So what we see is that the sources generally seems to follow this trend, but we also see some scatter. So the idea is that this scatter that we see for sources having similar luminosity should probably come from differences in the quasar lifetime. But really, all of these objects, so are they all young? This is something we should investigate more, and we are going to investigate more, because these are a lot of sources. So for example, one possibility is that what about maybe the presence of absorbers, which are truncating prematurely the proximity zone and then faking the shape of the proximity zone. So stay tuned, because this is something we are investigating. Then I want to show you another results. This one is a kind of the same plot, but the other way around. So we have the RP as a function of redshift, now color-coded with the luminosity. And here, what we see mainly is that with this work, as I said at the beginning, we are pushing the limit to higher redshift. So we are placing constraints in this part. But actually, people with this plot usually want to understand whether there's an evolution of RP with the redshift. Do we see an evolution with redshift? I don't really see an evolution with redshift. So usually people say that there's a shallow trend. I'm not sure about that. Anyway. So I don't know how much time I have. Okay. Okay, perfect. So I want to spend the last 5 minutes of my talk talking about some preliminary results, which we are currently working on. So what is the idea behind what I'm about to tell you? So now we have this measurement. We also want to figure out what is the probability of having a quasar with a certain proximity zone. So we want to investigate what is the probability distribution function. So then what we have to do is compare the real data with some simulated data. That is what I'm about to say. So what do? We take simulations, for example, the mixed one, on which we draw density and temperature skewers. We get 24 centimeters fast, and then we post-process all of them with 1D radiative transfer simulations. Then we generate mock spectra. In particular, these mock spectra I'm about to show you are just created assuming redshift around 6.8 and JAB magnitude 20.4, but this is just because we targeted one specific case. The final idea will be to have this kind of analysis done for the entire sample we are considering. So we will extend this work to all the sample. Then we also consider a different combination of fractional neutral hydrogen and quasar lifetime, because as we have seen at the beginning, there's a degeneracy between these two parameters. And then finally, once we have done this, we can perform on the mock the same kind of analysis performed on the real data. This is an example for one mock. So we have the spectrum of the mock, and then on the mock, we run the principal component analysis and we recreate the continuum. Then finally, we apply the definition of the proximity zone and we measure the proximity zone for the mock. We do this for all of them. And finally, we create this kind of plot. So here we have, as I said, the probability distribution function of these proximity zones, comparing the mock and the data. The data in particular in this case are just 6 quasars, because we want sources spanning roughly in the same redshift and luminosity range of the mock. So here in red, these are the data. And then we have 2 different sets of mocks, because we are creating them, as I said before, assuming different combination of fractional neutral hydrogen and quasar lifetime. And then we get this distribution. Here, just to help you out, I've put this box to show you what is the expected direction that we expect the histograms for the mock to move in case we change these parameters. This is like a reminder of the formula of proximity zone size. But this plot leaves me with a lot of open questions for the moment. So what do we learn here? These are real data, and they have very small proximity zones. So again, are these sources young? Or maybe there's something more we should take into account. For example, considering a model to describe the quasar like a blinking light bulb. So the quasar is not just a light bulb that turns on and that's it. It turns on and off. And then, of course, when it turns off, there are effects on the proximity zone size. Maybe. And then also, what do we learn here about the fraction of neutral hydrogen? So I'm basically concluding my talk with open questions, but stay tuned to know more about this work, because we're working on this. And I want to leave you with my take-home message, which is basically a summary of what I said today. So we have this sample of 45 objects at redshift higher than 6.5. If you're interested, just go check out the paper. Here we have created a composite spectrum, so an average spectrum that doesn't show changes with composite spectra created at lower redshift. And then finally, we perform on this sample, on 35 objects in this sample, a proximity zone analysis. We get this measurement, which are in agreement with the literature, but also they leave us with open questions like how many young quasars there are for real. And these are just sorry. And these are just like wish for the future about the other future work we would like to do with this data. So we would like to place constraints on the fractional neutral hydrogen and investigating the radiative efficiency of supermassive. Thank you. Questions?
So you go back to the result about the proximity zone versus absolute maximum.
Yes.
You see a large dispersion, but
yeah.
if you want to quantify this dispersion in terms of uncertainty on the time scale of the crystal, which value would you derive?
Not sure.
I mean, you said that maybe the differences are due to the TQ.
Yeah.
Okay.
Yeah.
So if you compare the maximum dispersion you have on the y-axis,
yeah,
what would be the uncertainty on the TQ?
Okay, so this is the next step that for the moment we don't know yet, but probably we need to pay attention to this kind of plot. So right, so we have a certain measure. I don't know if maybe this goes in the direction of the answer to your question, but so we have a certain proximity zone. We know that the scatter is probably due to differences in the quasar lifetime, and we should take into account a certain distribution, a certain like model for the IgM. And then, for example, if we are assuming an ionized IgM, as you can see here, we would have a huge error bar. So, but really, this is something we haven't discussed yet in my work, because it's the next step. But we can also chat more about this. Maybe you can give me some.
Other questions, Fabio?
So on the relation between with redshift, we see this ratio. Of course, each quasar will have its own.
This one?
Yes. Lifetime and the topology, the material.
Yeah.
It's different, but can you use like composite spectra in this redshift to get some average, value for RP in this direction? Maybe this scatter will shrink, or the difference in each quasar is just too big, so you would basically wash out every feature of this.
This is something I haven't thought about. Sure. How would you use the composite spectrum?
Is it to try and estimate kind of the average value? I mean, repeating your analysis on the composite spectrum.
But the composite is just a stack, right?
That's right.
So, I mean, it's a stack. You're not saying something on how that quasar behaves.
Yeah, but on the population of quasar that fresh. I'm not sure if you start them, you get the average answer, or you get something completely wrong.
Maybe this was already something that was done. I mean, she did something like that, right? Yeah. So yeah, some way, yes, but you cannot really say something on the quasar lifetime, right? Because it's a stack of spectra.
Yeah, on the single quasar.
Yeah.
Not the average.
Yeah, but yeah, this is something that was actually already done.
Okay.
It was Domenica Durovchikova, the fire cycle. She did that kind of, yeah.
There is a question from online. Let's see if it's posted or not. View. Okay. I don't know if we have the audio on here. Let me see.
Can you hear me?
Now we can hear you. Yes, please.
Okay. Now, my question is, you showed that the relationship between the proximity zones and the age of the quasar, and very interestingly, the lifetime turned out to be very typically relatively short.
Yeah.
At the same time, you have indications about the mass of the supermassive black hole, which are relatively large. So, in your what is your picture? You just hinted it at the end about the flickering light bulb.
Mm-hmm.
I mean, what does imply in terms of the seeds of these quasars and the evolution of the black hole mass function?
This is the big question. This is something we want to investigate, because my idea would be that if we try to focus, not really the mass of the black hole, but try to focus, like, for example, on the radiative efficiency, we can try to infer something on what is the duty cycle of the quasar. And so trying to figure out whether how the quasar is behaving in shining and not shining. And then, of course, try to link this with what is the expected behavior in the proximity zone. Because when quasar turns off, then with time, depends on like the equilibrium time, then the size of the proximity zone starts to decrease. So.
Yep. And I mean, from this TQ that you show, that they are extremely short, no?
Yeah, they seems to be very short. Yeah.
They're very short. And they are of the order of the time scale of the ionization time scales, basically. So it's like the stronger sphere recombine. very short activity with the stronger sphere recombining afterwards quickly, let's say on these time scales.
Yeah.
So this I don't know whether you agree, but this would imply then a low duty cycle and as a consequence, a slow evolution of the luminosity function at high redshift. I don't know whether everything is consistent in the picture at the end.
Like this is actually something I was discussing in my group because I agree with you, and like how can we actually place constraints on that? So my idea would have been to try to target, like for example, oxygen-tethered nebulae, which are more stimulated by quasar activity and they are more responsive, and try to see from that what is the status like in a short time of quasar activity, and then try to infer something on the duty cycle.
Yep.
Yeah, thank you.
Thank you. No, these data are really very, very, very interesting. Thank you.
Other questions? Ivan?
As a curiosity, maybe I missed it, but can you get constraints on the quasar lifetime or directly on the proximity zone size from cold gas measurements of the host galaxies of these quasars or galaxies around these quasars to see if this ionizing gas can coexist with cold gas, and I don't know, if it can help you
I think
placing some boundaries.
probably the problems are like the distances, right? Because proximity zones are really next to the quasar, so the host galaxy is on much more broad distances. So I don't know if you really see effects on the host galaxy.
But you're talking about many parsecs, so
Yeah.
If there any nearby galaxy, like sort of over density around these quasars, this will be then within the proximity zone. And I'm wondering if these galaxies could have some cold gas which can help you place some limits on the quasar lifetime, or I don't know, try to guess what the size, if the size that you measure is consistent with the presence of cold gas and not within the parsec distance.
Yeah. I don't know. We haven't done that, so we haven't discussed that, so I'm not sure.
Any other last question? No? So let's thank the speaker again.